Hello, good day. Welcome to study number 6 on moments of inertia and the parallel axis theorem. Moments of inertia and the parallel axis theorem. In the previous studies, we looked at moments of a force about a point, moments of a force about an axis. We looked at first moments, which we calculated by eliminating the ratio of the weight per unit volume. So that's the gamma factor and the thickness of our two-dimensional plates. In this study, we will extend the concept of the first moment into a moment defined as the second moment. The second moment is what is termed the moment of inertia, even though that term is mostly applied when we have masses. So let's get to the definition of the moment of inertia of areas, which is the second moment. Right, so the moment of inertia of areas is explained through 4 principles. It's explained through 4 principles. The first is a definition, right? The first is a definition of the second moment. The second is the moment of inertia by integration, and then the polar moment of inertia and the radius of gyration. The radius of gyration is an important concept you will use in dynamics, and the moment of inertia of masses, you also use it in dynamics. So this is its cradle, and we need to grasp as much as we can as far as this theorem is concerned. So the moment of inertia of areas is what will be defined first through the concept of the second moment. Right, in this study, the idea is that we've got a force that is variable. In this study, we've got a force that is variable. Do you still remember distributed loads? Distributed loads, we had some force which is variable. We had a small letter w that represented a force that varies with length or with depth. So we also had examples of dam walls which showed a distribution of pressure with depth. Right. So figures 9.1 and 9.2 are showing us arrangements of a beam and a dam wall. In these two arrangements, what is common is that we have forces which have a magnitude that depends on the height at which you measure the forces. On the right hand side, on the dam wall, these forces are height dependent because of the pressure. On the left hand side, these forces are height dependent because of the pressure, again, that is exerted on a beam. So figure 9.1 is an example of forces on a cross section of a beam which is subjected to equal and opposite couples. So on one end, this beam has a certain couple in a certain direction. Then on the other end, this beam has another couple in an opposite direction. So if we were to draw this beam, let's just say if we were to look at it from end to end, we could see something like this. So what we have on this beam is couple number 1. So I will just use the direction of this force to represent the forces on top of this beam at this point. Let me call this one minus F1 so that the force at the bottom, I can call it F1. So that would represent, let's say, that force. These two forces which form a couple, they generate a what? A clockwise moment at this point of the beam. Sorry, an anti-clockwise moment, which is a positive moment at that point of the beam. On this other side, we will have a beam end where we have a moment that is in the reverse. So we've got a couple that generates a moment in the reverse. So let's generate a clockwise couple. How can we do that? We need a force in this direction. Let me call it F2. And then another force in that direction, minus F2. So you will notice that the top forces, they are squashing or compressing the beam. The bottom forces are extending the beam, or the beam is in tension. So you will notice that from this point, you've got forces pointing it in another direction. And as we move up this axis, as we move up the y-axis, because we are squashing the beam, if we were to just exaggerate the extent to which we are squashing this beam, we can actually see some profile. So I'll try to draw it here. So I will just exaggerate and say this is the beam and this has been squashed. And this is that end which we were squashing, which has caused the beam to be compressed, and then at the bottom it has been extended. So the forces that we are applying are being transferred by the principle of transmissibility in that format. So the forces are transferred in that format. As you can see, from a common axis that is somewhere in the center of the beam, the forces have a magnitude which depends on the height at which we are measuring them. So this is depending on the height at which we are measuring these forces. In other words, these forces are height dependent. These forces are height dependent. How can we see the height dependence of these forces? This becomes just like that distributed load. Our distributed loads were looking something like this. And then we had some forces. This time they were pointing in the downward direction. When we had a beam, a dam wall, we had a profile of the distributed load in that direction. This time we just have the same as that of the dam, but these forces are actually acting on a cross section of a beam. So because we have a distributed load, it looks like a dam wall. Therefore, we can actually think of the forces in terms of pressure. So a small contribution of the pressure on this beam cross-section is simply defined by the contribution of the force per unit area. So these are the area elements on which some force is exerted. But we can see that that pressure depends on the what? On the height. So it is proportional to the height y from some axis. So that was the y from some axis. So if it is proportional to some height y, then we can use a constant of proportionality. So one special property is that they are linearly dependent on this distance, these forces. So that is one special property which justifies us to imply that therefore delta F over delta A is actually equal to Ky. Delta F over delta A is actually equal to Ky. And if we rearrange the equation, we will see that your small force contribution is actually a function of height and cross-sectional area. It's actually a function of height y and cross-sectional area. Height from some axis, cross-sectional area of the area element. If we have then a force that is defined in terms of delta F equal to Ky dA, we can find a resultant, which is simply a summation of all our delta F's from I is equal to 1 up to some number of forces. This means that on the right hand side we can equally sum up all these right hand side terms. So we now have a summation of Ky delta AI from 1 up to some n. So on that equation of the resultant, I think by now you can tell that you can use an integral method instead. You can now reduce these delta A's to very, very tiny infinitesimal area elements until we get an equation which looks like that. In other words, we've just replaced the summation process with an integral process. So now what we've done is to define a resultant force that is acting at the cross-section of the what? Of the beam distributed load profile. What is the moment of that force? And one other thing, before we even get to the moment of that force, look at that. Do you remember this parameter? We have an integral of y dA. Do you remember that parameter? I hope you do. Right. So this is actually k multiplied by what? A first moment about the x-axis. And as you can see, indeed, we are looking at a moment about the x-axis. Now, if we are to find the moment about the x-axis of this resultant, if we are to find the moment about the x-axis of this resultant force, let's forget that this force is dependent on y. Let's just write the equation. The equation for the moment will be what? Will be Fd, isn't it? Fd. So that will be the force multiplied by the perpendicular distance from the axis of concern, which is the x-axis. That is why we have this equation which states that delta m is equal to y times d delta f. Now let's substitute for delta f. We know that delta f is ky delta a. So now we have y multiplied by ky delta a, giving us 2 y's which square. That's why we have a ky squared multiplied by delta a. So in other words, we found a moment of the first moment. We found a moment of the first moment. This is clearer when we now find the total moment, which is capital M, which is an integral of that ky squared dA, and it's k multiplied by the integral of y squared dA. So if we were to write the integral of y times y dA, that is where we are now saying we are integrating the moment of the first moment. We are integrating the moment of the first moment. Hence the term second moment. Hence the term second moment. Now, because it is more applicable in engineering for masses, then it is more often than not referred to as the moment of inertia. So the second moment and the moment of inertia are mathematically the same thing, but the term moment of inertia usually refers to a mass moment of inertia. But at this stage, now that it has been introduced to us, we now know that the moment of inertia is simply the moment of a first moment. Then we can use them interchangeably because we now understand what's happening. Now, to introduce the meaning of these equations, which are exactly the same as what we had, we will look at a dam wall. We will look at a dam wall. Remember, for our dam wall, we have a pressure profile. So obviously, the small pressure contribution at that particular point is simply equal to the force per unit area. So that would be force per unit area. Now for dam walls, I think you still remember that we looked at at some of these definitions of this parameter, which we call the gamma parameter. And this gamma parameter was simply equal to what? It was simply equal to the weight over the volume. The weight over the volume. And we know that the weight over the volume, our volume is actually the area times what? Times the thickness. It's actually the area times the thickness. Thickness from where? Thickness from where? If you still remember the dam wall profile, we were actually looking at the depth or the height. So for that reason, if we make the delta F the subject, it becomes delta F is equal to the gamma parameter multiplied by the delta F. The gamma parameter multiplied by the delta V, multiplied by the delta V. And that is our delta V right there. So that's why I was saying the dam walls are better an explanation of the second moment. We are just now trying to find the moment of inertia of that, the first moment of that equation, and then the moment of that force, and then we find the second moment. So what we see in these two equations is that this k for the dam walls is actually replaced by a constant gamma. So it's one and the same thing. So if we have these forces on a dam that are defined by delta F is equal to gamma y dA. If we find the resultant, we simply integrate. So what are we doing? We're finding the resultant, which is equal to a sum of our delta F's, and this is equal to the sum of what? Of gamma y I delta A I is equal to 1 up to whatever number of elements that you may choose. So basically from this, we get an equation R is equal to, instead of us summing up, we will integrate using calculus. So that's why we now have what? Our gamma y dA, and then we can find the resultant force using this equation. To find the moment of that force, and by the way, this one we can already see that this is what? This is the first moment. We can already see that this is the first moment. So the moment of this resultant, which is actually a function of the first moment, is then given as the second moment, which is the moment of inertia. So instead of our k, we will just have our gamma, but by looking at these two, you can see a depth profile of the forces. So basically the load distribution, distributed loads are now invoked. They are now internally within this setup. They are now internally within this setup. That defines the second moment, which is the moment of inertia. Now, moments of inertia by integration is simply a second concept which seeks to make life easier if we have some shapes of these beams or these objects which are described by analytic functions. So if we have an analytic function which is a y as a function of x, a y as a function of z, whichever way, you can generally use your calculus using that function to then calculate the moment of inertia. So our moment of inertia has that symbol I. If it's about the x-axis, it's obviously y squared dA. If it's about the y-axis, it's obviously x squared dA. That is the meaning of equation 9.1. So since we are now using calculus, what do we need? We obviously need some tiny infinitesimal strips, area elements, which we will integrate, since we are integrating this function with respect to the area, right? So in this case now we're happy. We can now define our area element. The first area element that we have in this is a square area element. Why are we even looking for these area elements? So that we can define the y and we can define the dA. When we have done that, we can calculate the second moment or the moment of inertia. So you choose. These strips are, it's purely your choice, whichever way you are comfortable with. So if you choose a strip or an area element that is made up of a square, obvious, your dA is defined as what? As length times width, which is dx multiplied by dy by virtue of that orientation. Then how do you find your x? Your x is simply the x variable. How do you find your y? Your y is simply the y variable. So in this case, you've got your definition of the small contribution of the moment of inertia about the x-axis. Di in the x, what is it? It's y squared dA. What about di in the y? It's x squared dA. What is dA? It's a dx dy. So your square element has solved your problems. Here, though, you should be aware that you are introducing double integrals. If you don't want to work with double integrals, you can now use a horizontal strip or a vertical strip. So once again, what do we want to define? We want to define dA, we want to define the x and the y. So obvious that our dA is given as the length times the width. What is the length? The length is from A, subtract this x. So that is the length, which is A minus x. What is the thickness? What is the width? The width is dy. So our dA is A minus x multiplied by dy. Then this is the small contribution of the moment of inertia about the y-axis, about the x-axis. It's y squared dA. Then you just take your dA, you just plug it in there. Then you can integrate di in the x in order for you to get ix. And you can also differentiate ix to get your di in the x. It depends with what you want to do. Right, vertical strip, same applies. Our dA is defined as our y dx. So this is our y multiplied by the thickness of the strip, which is dx, because it's a vertical area element. So our moment of inertia about the y-axis becomes the x squared dA. Look at how these strips are being selected conveniently, right? So you choose a convenient strip Because if you want the moment of inertia about the y-axis, you're dealing with this x variable. Instead of you having to convert things using this horizontal strip, why not just use a vertical strip, right? If you use a vertical strip, you've got a known x position, whatever x is the actual variable, then you use it for the integration. Right, so basically those are how we would use vertical, square and horizontal strips to define our terms of the integration process to find the second moment. Okay, so conversion of one strip to the other, one type of strip to the other, this is just the same as what we had before, but it's useful. These are some of the useful tools that you can use to shorten the time that you take when you're calculating. So if we want to understand some of these strips, let's look at figure 9.4. Figure 9.4 is just showing some area, right? So this is representing the area whose second moment we want to find. But for us to find it, we need to integrate what the second moments of every small strip, which in this case is a horizontal strip. So this horizontal strip, it is defined, it has a thickness B, obviously, which is the thickness of this area. And then it has, it has a length B and a thickness dy, a length B and a thickness dy. So our dA is first defined as the length times the width, which is the B parameter multiplied by dy. So we now have our dA. So this means di in the x is what? Is the moment of inertia about the x-axis, which is y squared. So di in the x is equal to y squared dA. So instead of dA, we can now replace it with this b dy. So in the end, we actually have ix being equal to a third of b h cubed. This b came from the what? From the x parameter. This h came from the limit for the y height, so it was for the y parameter. Now, when you are looking at the use of a vertical strip, remember, a horizontal strip is easy for what? For moments about the x-axis, right? The same way we said when you look at this, it's easy to use this one for moments about the y-axis. So if you have a horizontal strip for moments about the x-axis, it makes life easy for you. So you now have this equation. But you can interchange. You can interchange depending on what you want to do. So now let's look at the moment about the y-axis. These are straightforward for the what? For the vertical strip. So for the vertical strip, your moment about the y-axis would be di in the y is equal to what? It's equal to x squared, not x bar. Let me just remove that. X squared dA. So what is your dA? Your dA in this case, your dA is the height y dx. So which is why you've got your x squared multiplied by y dx, which is that equation there. But what if you would like to use the vertical strip to find the moment of inertia about the what? About the x-axis. Remember, you already have a definition of the moment of inertia about the x-axis. It's already given here using a what? Using this strip. All we are doing now is we're squashing the strip. All we are doing is we're squashing the strip. So what are we doing? We can actually write it in terms of its variables, isn't it? Because our b, we said it's standing for the x parameter, our h is standing for the y parameter. So let's just rewrite that in terms of the x's and y's. So the moment of inertia about the x-axis for a strip, for any rectangular strip, is obviously now given by a third of x parameter y cubed. That is what we get as a general solution from this. Because all we are doing is we are now just changing the thickness of this strip. But the moment of inertia that we want is about the x-axis, which is the same. So we need to then differentiate this if we want it to be a di about the what? About the x-axis. So we will have a di in the x, d of ix dx, right? Being equal to what? A third of y cubed, and the first differential of x is just 1. So in the end, this implies that your di in the x can generally be written as 1/3 of y cubed dx. 1/3 of y cubed dx, which is the parameter that we see there. So you can use the same strip for any two axes about which you want to calculate the second moment or the moment of inertia. I think below here we just have the application of the same principle so that we can write these equations, which are what we saw there. Right, so we have an example here. We have an example where we want to determine by direct integration the moment of inertia of the shaded area with respect to the x-axis. The moment of inertia of this shaded area with respect to the x-axis. So you can choose as you wish, a horizontal or a vertical strip. We already have some equation for the vertical strip, so we can even make use of it. So let's just see how it works. So this will be our strip. This strip is how thick? It is dx thick. How tall is it? Its height is y minus 0. So that is its length. So if we were to define the dA parameter for this strip, our dA is simply equal to the height, which is y, multiplied by the thickness, which is dx. That's our dA parameter. This means if you actually want to find this, you can just use your y function because it's analytic. So that would be your k into x minus a all squared multiplied by dx. And if you want to find the area, you're simply integrating this k into x minus a all squared with respect to x. That's how you would find your area if you need to look for that. So let's find the di with respect to the y-axis. So our di about the y-axis is obviously equal to our x squared dA. Our di about the y-axis is equal to our x squared dA. So if it's about the y-axis, it's actually the easier case. So what is our x squared? Our x in this case is just a normal x. What is our dA? Our dA is, what is our dA? Our dA is y dx. So we actually have that as k into x minus a all squared dx. That would be our moment about the y-axis. So if you want to clean this equation, you can actually make use of, maybe you can use the limits of this equation where you have y is equal to, in fact, x is equal to 0 so that you find k, or where y is equal to 0 so that you find k, so that you can write your k in terms of the parameters a and b, and then you've got your equation. So in this case, it means that your iy is simply now equal to the integral. Let me put the k outside. You will already have found what k is, right? And then you can write your x squared into x minus a all squared multiplied by dx. What are the limits with respect to x? It's from the origin up to a, and you're done with your moment of inertia of this shaded area with respect to the y-axis. The second concept, or the third concept on the moment of inertia, is the introduction of what is called a polar moment of inertia. A polar moment of inertia. Right, with a polar moment of inertia, what is happening is that we've got some shapes, right? We've got some objects which are best described by polar coordinates. So this could be curved, this could be cylindrical, and so forth. So I think you still recall the basics of your polar coordinates. Your polar coordinates are simply in the x, y conversion system. So you're converting your xy into an angle theta and a radius, which is actually a magnitude of the hypotenuse. Yes, of the hypotenuse. Okay. So we've got our x-axis, we've got our y-axis, and then we choose to define these now. We choose to define these in terms of a hypotenuse r and the angle theta from the horizontal axis. So if you look at these equations are just telling you that your y is simply equal to your r sine theta. Your x parameter is your r cos theta. So this is basically y over x is a tan theta. And your tan theta is simply, your theta angle is now an arctan of that. And obviously your r squared is equal to what? X squared plus your y squared. That is the definition of your polar coordinates. So you can actually find a moment of inertia of some area in terms of polar coordinates. So the distance r used to evaluate the polar moment of inertia is what is shown in this diagram. So this is where you would have put your area element dA. You are now describing the position of area element dA using a magnitude r that is a straight line away from the origin but oriented at some angle theta. So your polar moment of inertia in this case now is given by r squared dA. Why? Because your r squared is your distance from the distance of the area element from the axis of concern, which is the origin, which is why we have it as O there. So yeah, r squared, we've already defined it. It's x squared plus y squared. So if we substitute this x squared plus y squared in there, you will notice that we will get an equation which looks like this. Our polar moment of inertia about the origin O is simply equal to the r squared dA, which is an equation that looks like what we had earlier, which was y is equal to, let's say, x squared dA, and we integrate. So this is now our distance r. So if we then substitute this into there, into this r, then we obviously are trying to expand the bracket x squared plus y squared close bracket multiplied by dA. So by expanding this distributive property, we will find the first term is y squared dA, the second term is x squared dA integrated. If you just look at that, this is obviously your what? Your second moment about the x-axis. This one is your second moment about the y-axis. So it's exciting to notice that equation 494 has actually been systematically derived for us. We can tell where this is coming from. And why do we need the derivations? Because you will need to start figuring out which parameters should I use for this case. So which means that would be necessary. So polar moment of inertia, we've got an example where we have an object. Remember, the polar moments are all about these objects that have some men of curvature. So if you look at your textbook, it will actually put this in better words. So the polar moment question reads as follows. Determine the polar moment of inertia and the polar radius of gyration, right? The polar moment of inertia and the polar radius of gyration of the shaded area shown with respect to point P. I think we already had the radius of gyration defined. Right, I do not see the definition of the radius of gyration here. Right, radius of gyration, I think we already had some equation which defines the radius of gyration as a kx squared would be equal to your ix over the area, ky squared would be equal to the iy over the area. But I think we'll get there in this set of slides. Let me just first calculate then for this question just the polar moment of inertia. That's all we want, just the polar moment of inertia. The second part is in the next slide, so let me skip that. So if we want the polar moment of inertia, we know just that the polar moment of inertia in this case is about the point P. It's given by what? We are in the xy system, so we don't have an r, we don't have a theta, so we can easily make use of the rectangular system because we've got a conversion system for that. So that's just a sum of our ix plus iy. So what is ix? What is iy? Now, this is where we need subscripts. This is where we need subscripts because we know that for us to get ix, we need to first figure out this expression. What is dix? We know dix, this is the moment of inertia about the x-axis, the moment of inertia about the x-axis. If we have a vertical strip and we are dealing with the x-axis, what did our equation say? What did our equation say? 1/3 of what? So this is a vertical strip and we're using the moment of inertia about the x-axis. But this time we're using a vertical strip. So that's 1/3 of y cubed with respect to x. 1/3 of y cubed. So we have this. 1/3 of y cubed with respect to x. That's our moment of inertia of a vertical strip about the x-axis. How can we define our y's now? Our y is obviously this function, let's call it y1, so let's put a subscript there, and then the bottom function, let's call it y2, we'll put a subscript there. Right, so our equation obviously becomes equal to 1/3 of y, let's say y1 is the one at the top, isn't it? y1 cubed, right, minus 1/3 of y2 cubed with respect to x. That is our moment of inertia. Just the same way we were adding up, we are now finding the difference just because of the arrangement that we have. Okay, so you now have an expression. So what is y1 and y2? We know that y1 is simply equal to c plus k2x squared. Okay, so I suggest that if you have all these parameters, convert these extra constants. So use your algebra, use your graphical techniques to convert these extra functions, sorry, they are not functions, constants into the given variables for these sides, a to a. So in other words, we want what is c in terms of a, what is k2 in terms of a. Right, and then we have y2 at the bottom, it's equal to k1x squared. So okay, in actual fact you could name this one 2 just because it has a k2, but I've just reversed it. I'll leave it like that just for now, because in any case you can see the labels in this set of equations. So you already have these equations, so you will do the rest of the algebra, which will be just 1/3 of that function y1. This is now assuming that you've already converted the c and the k2 into what? Into their terms of a, So that would be c plus k2x squared. This is cubed minus, let me not put another 1/3, let me just put this cubed function. What is the second cubed function? y2 is k1x squared. That's cubed, then with respect to x. So it means that we have a function which can actually integrate, because all these are constants, You then find your ix. When you found your ix, the next thing is to find your iy. So what is diy? I think we've seen that diy is simply equal to x squared dA, isn't it? X squared dA. You can just cross-check that here. X squared dA, yes. Our dA is the y dx. So this is now meaning that we've got an x squared, our dA is y dx. So what is y dx? dA is equal to y times dx, but we know that our y is actually equal to the y1 minus the y2 dx. So that would be y1 minus y2 dx. That's your function. The y1, we know its function, it's c plus k2x squared. The y2 function, k1x squared. We subtract them, we obviously find x squared now being multiplied by a function of what? Of x only. So that would be c, it should be some a or b, plus k2 x squared. This k2, you will have converted it, minus y2, which is k1x squared. and I think then you are safe. You can proceed with the integration, because all you need is now your I in the y is now equal to an integral of this whole term there. Right, so basically that summarizes your Ix and the Iy. So if you would need to find the area, it's obvious for the calculation of another parameter. I've not introduced it, so let's not get there. So this is just the first part. So which means your J about P is now your Ix plus your Iy. What is your Ix? It's an integral of this equation. And then what is your Iy? So let's just say integral 1. Let me just remove that. And then plus I2, which is this integral. Right, so that sums up your calculation of a moment of inertia. This was just a polar moment of inertia. Now this term that was specified in the earlier slide, radius of gyration, so this is where it is actually defined. So that's why I did not end up attempting it. I actually did not pick a correct, in fact, the right question, because it's asking for something that is now advanced. But in any case, it was the next slide, so no big deal. So there we have it. Radius of gyration is a very important parameter. Remember, when you're doing dynamics, this is one of the parameters that you'll be playing around with it as if it's just your bike, or it's something that you know inside out. So let's make sure we've got a good idea of what's happening here. So the radius of gyration is a very crucial parameter. When we are looking at some given object which has some area such as shown in figure 9.7a. So if we have some object with some area as shown there, basically we can tell that the area is irregular. The area is irregular. Now, if we were to find a way, so for this object, we can actually find the moment of inertia, let's say, about the what? About the x-axis or about the y-axis. Now, if we are to compress this area, if we are to squash it and to make it a very nice horizontal strip, so we are not creating a horizontal strip in it, we are squashing the area, or we are generating a geometry that is parallel to the x-axis. The parameter, which is the point at which we can place that area in such a way that we will get the same moment of inertia as what we had when we had the area like that, and we changed it, and we used the methods that we had before. We found some area element, we integrated it. If we can find a convenient point to locate this whole area to find that moment of inertia, then that point can only be what is called the radius of gyration. That point can only be the radius of gyration. So if it is the radius of gyration about the x-axis, it's called a kx. This is where you would have found your moment of inertia of this object about the x-axis. Then you want to squash the object and put it at some point in order for you to obtain the same moment of inertia. That point can only be the distance kx, the radius of gyration about the x-axis. So that is what it physically means by definition. The same applies for the radius of gyration about the y-axis. You will have squashed this object, squashed it. But instead of making a horizontal strip, you make a vertical strip, and you place that strip just the same way you did here. You placed it equidistant so it's centered on the y-axis, but it's parallel to the x-axis. This time you center it on the x-axis, and it's parallel to the y-axis. If you squash it and you place it there, the moment of inertia that you got when you're calculating this part can only be located if you move it and you squash it and you place it at the radius of gyration, ky, right? So this is still our area A. The same applies if you were to fold this into a circular strip, then it can only have a radius called the radius of gyration. In actual fact, when we are speaking polar, it actually makes better sense. It actually makes better sense. So basically, that is the definition of the radius of gyration. Equation number 5 is basically introducing the term radius of gyration that we can find when we are using this Ix. Obvious, we know that Ix is what? Ix is our x squared. In fact, dix is our y squared dA. Yes, dix is y squared dA. So in this case, if you look at it, if we want to find the moment of inertia about the x-axis, the y squared, the distance in the y, is actually known as what? As the kx. So it's well, ask Bia, guys. I don't know why Bia chose to put kx, but actually it sort of assists you to denote the axis about which you want to find that radius of gyration. So basically, from this equation, we are just replacing the y variable, which in this case is now the what? The k. That is why this k is what? Is squared when we perform the integration. When we integrate, we just have a k squared dA. K squared, and then we multiply by the integral of dA and get an a. So by definition, then the radius of gyration about the x-axis is simply equal to the square root of the moment of inertia about the x-axis divided by the area. Right? So this is where you can actually conveniently use your dA, because if you have a dA, then you can actually integrate it to get an area, and then you've got your radius of gyration. Right, the same applies for your IY is simply ky squared, y, because our diy was x squared dA. Our diy was x squared dA. So this is for this particular case. Our x distance is now represented by ky. So if it is represented by ky, this is what is there. We square it, we integrate, and then we get an a. Therefore, the radius of gyration about the y-axis is ky, which is equal to the square root of iy over a, which is equation 9.6. Equation 9.7, no-brainer. You already know your definition for the polar moment of inertia. So if we have the polar moment of inertia, then it means if we have the polar moment of inertia, what has happened to my slides? No, we're still here. Okay, we are here. Okay, sorry. So we were here. So what we just have there is just a replacement of the radius, which was what? Which was r with k, and then we can find the polar radius of gyration. So this is how we can actually end up relating them, because we can tell from this set of equations. We can tell from this set of equations that this as what is common is the area. What is common is the area. So in the end, your k not squared is equal to that plus that, just because your j is equal to ix plus iy. Right, so generally this is what is known as the radius of gyration by definition. So if we want to find the radius of gyration in this question, determine the moment of inertia and the radius of gyration of the shaded area. I think with this question, it's a matter of the moment of inertia. That's the most important thing, because the radius of gyration equation is a simple one. So just quickly, moment of inertia, they say what? With respect to the x-axis. Thank you. So it's not much of a lot of work. So we want to find I in the x, so that we can find kx, which is equal to the square root of I in the x over the area A. So what is di in the x? Di in the x, again, we can see that this is a vertical strip, but we want to find the moment of inertia of this vertical strip about the x-axis. So it's obvious that it has to be 1/3 of y cubed dx. Right, that's our di in the x, the general formula. So we will then write it as di in the x is 1/3 of y. Are they labeled? Yes, these are labeled y2 and y1. So that's y2 cubed minus, yes, we want to find y, minus another third of y1 cubed dx, isn't it? Yes. So we're happy, we've got that. The functions, are they defined? Yes, y2 is k root x, k2 root x, y1 is k1x squared. So this is obviously equal to 1/3 of y2 is the k2 root of x. This is now all cubed. So let me just do it this way. And then minus y1, we said it's k1x squared. So that is a k1x squared all cubed with respect to x. You can express your k's in terms of the parameters what? A and b. Express your k's in terms of parameters a and b. Then you can find your I. So let's just write the I then. The I, which is the integral, is simply that integration from what? From 0 up to a. From 0 up to a. And then you find, let's just call this one your Ix. So if you want to find your radius of gyration about that axis, all you need is your Ix divided by the area. Ix divided by the area. And how would you get this area? How would you get this area? Remember the definition of dA, isn't it? So you're looking at that strip. The definition of dA is our y, in this case is y2 minus y1, that's the length. The thickness is dx, isn't it? Yes. So obvious, your a is simply the integral of dA, which is equal to the integral of those functions. So y2 is a k2 root of x, k2 root of x. Minus k1, I don't need to put the brackets. I can put this one and say minus k1 x squared. Then we can close that bracket. This is from 0 up to a, and this is with respect to x. So that's there. So then you find your area, and then that's what you use to then divide that equation and find your radius of gyration. Radius of gyration. So what are we doing when we are calculating radius of gyration? We just want to find the equivalent distance from whatever axis about which we want to find the moment of inertia. That distance must be equivalent to give us a moment of inertia that is the same as taking that other object without folding it and finding the moment of inertia about that axis. That's your radius of gyration. Right, so now let's move to the second part, which is on the parallel axis theorem and composite areas. The parallel axis theorem and composite areas. This section is introducing a concept that can make life very easy for you as engineers. The structures that you're dealing with are huge. The structures that you're dealing with have too many axes to think about. And they're in space. There's no way where you can get to a shipyard and you will see some point which they say, this is the origin. So in this whole shipyard, this is the origin. So all your beams are measured from... the material will be all over the place. Right? Even if you've completed the building and this thing is now moving and you want to find its moment of inertia for whatever reasons, which are now in dynamics, for example, the orientation is all over the place, right? Origins and rectangular coordinates are defined. So you define them because you now know what they are. So we need this centroid-based theorem that can make life easy for you to find the moment of inertia. So it's summarized in two principles: the parallel axis theorem and composite areas. So if we have composite areas, remember what we can do? We can use tables, right? It means tables are coming. Right, so this is the definition of the parallel axis theorem. Consider a body whose moment of inertia you want to calculate, or for which moment of inertia you want to calculate. So this body has some area element dA, and obviously you can use a square area element, you can use a horizontal or a vertical area element. Now, this body is located somewhere in space, but this somewhere is a distance d. The centroid of this body is a distance d exactly from some axis a prime. So remember, we said this is in space. So what we know for sure is that its centroid is a distance d from some axis a prime. Then the area element that you choose is at some other distance y prime from the centroid, so that the absolute position of the y of the area element is y. Now, if you want to find the moment of inertia of this body about the A prime axis, remember now we are no longer talking x and y. This is real life now. This body is somewhere and we just want to use what we know, which are these parameters. So for us to calculate the moment of inertia about the A prime axis, this is where we can use this theorem. So by definition, first of all, when we are looking at that diagram, by definition, we know that the moment of inertia of this body is calculated by y squared dA. Why are we saying y? Because we are dealing with the y-axis from which we are measuring the location of this body. So that's what we have there. So that's why we're choosing to use I about the AA prime, AA prime axis. It's y squared dA. Perfect. Now, our y squared dA, if you look at our y, the parameter y, in this case, our y is simply equal to the sum. Y is the sum d plus y prime. Y is the sum d plus y prime. Because we have y prime plus d as the y, then if we put it into the equation for the moment of inertia about A prime, we get the equation, the integral of y prime plus d all squared. Y prime plus d all squared. When we have this, then we can freely expand our integral because we know that this is a summing process. So we know that if we expand this bracket, we will simply have a y prime squared plus 2y prime d plus d squared. So since this was multiplied by dA in an integral, then we will just split the integrals. So we will have this first term. This is this first term. That's your y prime squared dA. This is our second term. It's a plus 2dy prime. 2d, d is a constant, so we pull it out of the integral sign because we are integrating everything with respect to a. So we can pull it outside, and then we have a y prime dA, and the last term is where we have the d squared out of the integral, and we only integrate dA. So as you can see, what can you see in equation? It's not written. So what can you see in this equation? There are some terms that are very common that we are used to. This term, we've been playing around with it, isn't it? This term, we've been playing around with it. That is the moment of inertia. That's the moment of inertia. And if we are looking at the distance from which we are measuring this y, can you see? It's from the centroid, y prime. So therefore, it is defined as what is called the centroidal moment of inertia. The centroidal moment of inertia. This one. That's our centroidal moment of inertia. How about this one? This is the moment, the first moment, isn't it? Y prime dA. This is the first moment. And the last one, this is just an integral of d squared, d squared integral of dA. So obviously we'll get a what? A d squared multiplied by a. So what happens to this term in this equation? What happens to this term? If you look at that integral, that's a y prime dA. So this is actually a first moment. This is actually a first moment. But this is the first moment about the what? About this axis. This is the first moment about this axis. And if you check, you will notice that that first moment, it simply adds up to what? To 0, because we don't have a distance about that point. So it will simply add up to 0. Look at what's happening even here. We've got another moment, so it will all add up to 0 if we integrate them. Right, just because we are about the x, we are about the centroid. So that principle that we discussed some other time, it actually comes in handy. As long as we are about the centroid, then all these moments will add up and cancel. So this is the parallel axis theorem. If you want to find the moment of inertia about some axis that you do not know, this axis is maybe written as A prime, and we know that the distance from that axis is d. You can now use equation 9.9, where you first find a centroidal moment of inertia and you simply multiply the area by this distance d of the centroid from the given axis. Therefore, you can find the moment of inertia about A prime, some unknown axis. Right, so by the same sign, you can then find the centroidal radius of gyration, which is k bar. You can find the centroidal radius of gyration, which is k bar, and the polar centroidal moment of inertia. The polar centroidal moment of inertia. So basically, this is what we are seeing in these equations, the definition of the parallel axis theorem. So we are not going to be interested in other parameters. We can just use the parallel axis theorem. So this is a very good example of where we can tell that the parallel axis theorem is cool, because in this example, we want to determine the moment of inertia and the radius of gyration of the shaded area with respect to the x-axis. As you can see, this object is irregular, right? So obvious, its total moments of inertia need to be investigated. We need to actually calculate the moment of inertia and split it into different parts, right? So in your textbook, there are some tables. These tables will actually tell you that for a geometry that looks like this, which has some length and some width, the centroidal moment of inertia is actually given by whatever fraction, 1/3 of length, width squared, or something like that. So there are some equations that you can pull out from the tables. So this is where we are happy to now investigate composite areas that are made up of what? Of other geometries. So let's split, because we know we can add up all the moments of inertia to get the total moment of inertia. So that's object number 2, and that will be object number 3. So object number 1 is right there at the top. Object number 2 is right throughout this length. Object number 3 is right there at the bottom. Right, somewhere, something like that. Okay, so for us to find the moment of inertia and radius of gyration with respect to the x-axis, we know that our ix, right, it's about the x-axis, it's going to be equal to I about the x-axis of area number 1 plus I about the x-axis of area number 2 plus I about the x-axis of area number 3. Let's look at area number 1. I about the x-axis of area number 1. Area number 1 is some distance away. So if we were to look at what we had before, we can actually make life easy for ourselves by looking at area number 1 isolated. So if it is isolated, we can tell that its centroid is somewhere there. So that becomes our distance. That becomes our d from the axis that we want to find a moment of inertia about. So that is the d, which we found, remember, in our diagram. D is the distance from the axis of concern to the centroid. So we have found that d. And we can tell that this d is equal to what? It's equal to this 24 millimeters plus half of 6, that would be 3 millimeters. So this is in millimeters. Now we have the d. D for area number 1. What is the centroidal moment of inertia? This is a rectangle. So you can just find the central, the centroidal moment of inertia of a rectangular shape whose length and width are, this is L1, this is width 1. So there's some equation in your tables. You can pull that out. and you use it to put it there, plus the area of that is simply L1 times width 1. D squared is simply our D1, which we already found as 24 plus 3, which is D, and then we square it. Then we've already found our moment of inertia about some axis that is away from the centroid. For area 1, how about area number 2? Moment about the x-axis for area number 2. What is the D? The D is 0. So we need the centroidal moment of inertia for area number 2. Where can you get that? You can get your tables. They will tell you something like this. Centroidal moment is whatever fraction of the length and the width for a rectangle. Plus length 2. So this is object number 2. Length 2, width 2. The D, we said it's 0. So this term actually becomes a 0. Then you have your IX3. Your IX3. What is your IX3? By the same method, you just need your centroidal moment of inertia of object number 3 or area number 3 plus its area is obviously length 3 width 3, right? That's its area. This is being multiplied by the D. What is the D? The D is from there all the way to its centroid. So that would be D2 is equal to 24 plus, fortunately, another 3. So it's the same. So I can just put my D2 there. And this is a negative D2, right? This is a negative D2 because it's in the negative. But we're going to square it because all our moments of inertia are what are squared. So then it means that your total moment of inertia about the x-axis is your centroidal moment of inertia for area number 1 plus L1 W1 D1 squared plus centroidal moment of inertia for area number 2 plus centroidal moment of inertia area number 3 plus L3 W3 D2 squared, and you've got your total moment of inertia about the x-axis. This implies then that the radius of gyration, because they've asked us, the radius of gyration of this shaded area with respect to the x-axis, the radius of gyration with respect to the x-axis. We already know from equations that it's simply now the Ix over the area. How do you find the area? The area is simply equal to area section 1 plus area section 2 plus area section 3, which are simple length times width calculations. So you can find your radius of gyration. This you had already found in this calculation. Right, so for us to work with an easier system, we will consider composite areas where we are using our tables. So like what we discussed just now, if we have a rectangle, which is the basic geometry for all the shapes that formed 1, 2, and 3 for that section earlier on. So this rectangle, let's just check that. This rectangle has a base B, it has a height H, right? So if you want to find the moment of inertia of this rectangle about the x-axis, which is this axis, that is the equation, right? And I think you still remember from that derivation for that strip, we got something like that. However, in fact, it was in the textbook already. However, if we want to find the centroidal moment of inertia of that rectangle, there are some tables that already show that it's a 12th of base times height cubed. This means from the calculation that we made, we can simply take that and use those tables. So it also gives you, these tables are cool, they give you everything. Moment of inertia about the what? About the x-axis centroidal, about the y-axis centroidal, about the x-axis which is at the bottom if the geometry has a bottom, right? About the y-axis, same applies, and the polar moment of inertia. And remember, this is not a centroidal, this is JC, yes, so that's JC. So you can actually see that we already had JC defined where, there we have it. So JC was already defined here. About the centroid. Now these are figure 9.13 are very important parameters. So we've got a table that has beam cross sections. So one of the things that you'll notice is that with construction, the H section is the deal, right? The H section is the deal. So you've got different definitions of these sections. Some are called S shapes, some are called W shapes, and so forth. So if you are given some axes for reference, this means that you already have some name of the section. So in construction, in engineering, in electronics, you will notice that they are what are called part numbers, right? And for a particular object of a certain part number, there are certain dimensions that it has. So there are common objects which may not need a serial number. For example, H-beams that you may be using to construct a certain section. So if you are doing that, and this construction is not necessarily all construction in the industry where we are building with bricks. It also goes to things like Lego that you may use for a small robot, right? So all these sections and their dimensions will be standardized. So the standard designation of a section can be either in the imperial system of units or in the SI system of units. So you need to select the appropriate table. So this section, for example, is called a wide flange shape, W shape. This W shape comes in these dimensions, and you can check the textbook. It will show you what these dimensions actually mean, because they have something to do with your height and your width settings. So you will need to master which dimension refers to which side, right? So that applies to those. They have certain areas. This is the depth. The depth is also defined. So that's something, it's just a matter of reading off from the tables. So there's a defined depth and there's a defined width, and there are some x-axis moments of inertia. So moments of inertia about the x-axis, centroidal, radius of gyration, and if it has an x point at which we have a centroid, then you will get the corresponding y bar. You will get a corresponding y bar. As you can see, our y bar in this case, these are all zeros, just because this is the centroidal, so we are exactly at the center. It has two lines of axes of symmetry. The same applies about the y. We've got what? The centroidal moment of inertia about the y-axis, the centroidal radius of gyration, and this is located at the x is equal to 0. So we've got nothing for the x bar. So these are the tables that you can make use of. So an example is in here where you have two 20mm steel plates. These are welded on a rolled S section as shown. So remember, we had a wide flange shape in this table. Now if you go to this table, it will show you an S section. This time, use which table? Use the table for the SI system of units, because as we can see, we've got our distance in meters and we've got to use the SI system. So two 20mm steel plates are welded to a rolled S section as shown. Determine the moments of inertia and radii of gyration of the combined section with respect to the centroidal x and y axis. With respect to the centroidal x and y axis. So how would you do this? So you want to find the moment of inertia with respect to the x-axis. So obvious, you need the moment of inertia with respect to the x-axis of let's call this one area 1. Let's call the S section area 2. Let's call the bottom section or the bottom area plate area 3. So this is for 1 plus I about the x for area 2 plus I about the x for area 3. What is I about the x for area 1? What is I about the x for area 1? We've already learnt using the parallel axis theorem. Centroidal of the area 1 plus AD squared. So that would be D1. What is D1? look at what we're doing now. We are using part of this S section. So that's why it's important for you to know the parameters of the S section. So this is what we know is the D1. That will be D1. But we are not given this distance. So it means you need to now grasp the parameters of the S section, because it can give you that distance. When you have that distance, you're obviously now giving, so let's say this is equal to the S section's Y distance. So let me just say YS plus half of this thickness is actually 10 millimeters. So plus 10 millimeters. That would be your D1. So you now have your D1. What is the area? This is just length times width. So I don't have to really write that. It's just length times width of a plate. We're done. Then let's look at the second, which is the S section. IX2 is given by, obviously, the centroidal moment of inertia for area 2 plus AD for area 2 squared. What is the centroidal moment of inertia of an S section? The S section is the S310 times 47.3. So you now need to look at your tables. When you look at your tables, what are we looking for? Centroidal moment of inertia about the what? The X. Centroidal moment of inertia about the X. So this is where we would go for that S section. So you need to then identify the S section. And you should be dealing with the SI unit system. Then you get that, then you will write its parameters here. Let me just leave it like this one. Plus your AD. What is D? Right? So if this is the centroid of the S section, so you also need to look for the centroid of the what? Of the S section. If it is symmetric and it has an axis, what is it? XX axis, this one. If it's exactly about its center, then it means our D will be equal to 0. I will just write it here just in case it is not. D2 squared. Right, and then the last one would be IX, about the X of area number 3. That would be its centroidal, its centroidal moment of inertia plus its area times D3. Centroidal, what do? You just go to the tables. So let me just rewrite it as this. Plus, because this is a what? This is a rectangle, right? This is a rectangle. What is our area? I don't have to write that. This is a rectangle. You know this inside out. What is the D? The D is from there all the way to half its thickness. So they said these are identical plates. These are 220 millimeter plates. So it means you're going to have your Y, it's now in the negative direction, your YS, let's assume it's exactly the same, plus 10 millimeters. And then you can now add these up, get your total, then you get your radius of gyration by what? By the square root of IX over A. And this is basically the square root of the sum of all the moments of inertia from I is equal to 1 up to 3 sections all over area. Something like that. Right, let's just neaten this up so that it will look as it must. That sums up composite areas, and that sums up moments of inertia and the parallel axis theorem. Moments of inertia and the parallel axis theorem. So please, let's now be serious with making sure that we understand the details, because these are the details when it comes to your further studies. So we need to grasp this concept of the moment of inertia. It is just a second moment. The moment of inertia is just a what? It's just a second moment. That second moment is calculated in the same way we calculated the first moment. But in this case, we have a distributed load. So because the distributed load has forces which have a value that depends on the height at which you measure them from some axis, then we end up having to find the moment of a force that is distance dependent. In the end, we end up having the second moment, which is the Ix, or moment of inertia. If it's about the x-axis, it's given by y squared dA, and you integrate everything. If it's about the y-axis, it's the integral of x squared dA. If it is the polar moment, then you are integrating r squared dA. Each of these moments of inertia have an associated radius of gyration. And the radius of gyration is simply that distance which we need to locate a compressed version or a compressed geometry of the original area parallel to the axis of concern, such that we get the moment of inertia that is exactly as we would find for that original area. That sums up this chapter. So let's, in fact, these first two sections of the chapter. We still have 4 more sections to go, so I've got 3 more lectures. So all the best, and I wish you a relaxed weekend while you play around with the moment of inertia. All the best, and it's a goodbye.